If your model gives bad answers about your business, the problem may not be the model. It may be that you are using the wrong customization strategy. Today, we will learn how to tell the difference between RAG, fine-tuning, and LoRA. 3 paths, 3 different philosophies. One goal, making AI work for your specific domain. There are 3 major paths to customizing a pre-trained language model. Retrieval-augmented generation, or RAG, gives the model access to external knowledge without changing its weights. Think of it as giving the model a library card. It can look up facts, but does not learn anything new. Full fine-tuning updates all model parameters on your domain data. Think of it as sending the model back to school for a specialized degree, expensive but transformative. And LoRA, or parameter-efficient fine-tuning, trains small adapter modules while keeping the base model frozen. Think of it as plugging a specialist tool into a working machine, efficient, fast, and reversible. 3 paths, 3 different philosophies. The right choice depends on what your problem actually needs. Before any customization, data must be prepared. This starts with tokenization. A tokenizer converts raw text into numerical token ID, the only language a model understands. For example, the sentence "this movie is great" becomes a sequence of 5 numbers. The model also needs an attention mask to know which tokens are real and which are padding. Padding and truncation ensure all examples in a batch have the same length, like making sure all books on a shelf are the same height so they stack neatly. Data preparation is the foundation of everything. If your data is poorly formatted, no customization strategy will save you. Garbage in, garbage out. BERT-style models are encoder-only transformers. They are designed for understanding tasks, classification, prediction, and extraction. You feed in text with special tokens like CLS at the start and SEP at the end, along with input ID and an attention mask. The model processes the entire input and predicts a label. For example, classifying a movie review as positive or negative. BERT does not generate new text. It reads, understands, and decides. Think of BERT as a careful reader who highlights the answer in a passage rather than writing a new essay. GPT-style models are decoder-only transformers. Unlike BERT, they generate text 1 token at a time, predicting each next word from the context that came before. Training data consists of prompt completion pairs. You combine the prompt and the desired completion into a single training sequence, and the model learns to predict the continuation. For example, given once upon a time in a faraway swamp, it learns to continue with "there lived an ugly orc." The key difference from BERT: GPT writes new text, BERT classifies existing text. One is a writer, the other is a reader. Retrieval-augmented generation, or RAG, does not train the model at all. Instead, it builds a searchable knowledge base from your documents. Here is how it works. First, documents are split into smaller chunks because models have a maximum context length. Then each chunk is converted into a dense vector embedding, a list of numbers that captures its meaning. These embeddings are stored in a vector database like FAIS. At query time, the user's question is also converted to an embedding. The database finds the most similar chunks, and those chunks are passed to the model as context. The model then generates an answer grounded in those retrieved sources. Think of it as giving the model an open book exam. It does not need to memorize facts, it just needs to know where to look them up. Vector search finds content by meaning, not just by matching keywords. If you ask he throws webs, a keyword search would look for the words throws and webs. But a semantic search understands that this question is about Spider-Man and retrieves Spider-Man facts. The embedding model converts text into vectors in a high-dimensional space where similar meanings cluster together. This is why RAG can retrieve relevant documents even when the exact words do not match. It is not searching for words, it is searching for ideas. Full fine-tuning continues training a pre-trained model on a smaller, domain-specific dataset. Unlike RAG, fine-tuning updates all the model weights. Think of the model's 124 million parameters as tiny dials. During fine-tuning, every single dial gets adjusted to reduce errors on your specific task. This teaches the model entirely new behavior, how to classify clinical notes, summarize legal contracts, or generate code in a niche framework. But it comes with real costs. You need hundreds or thousands of labeled examples, significant GPU compute, and careful evaluation. And there is a dangerous pitfall called catastrophic forgetting. If you train too aggressively, the model loses its general knowledge while gaining the new specialized skill. It is like a doctor who studies cardiology so intensely that they forget how to treat a common cold. LoRA solves the cost problem of full fine-tuning. Instead of updating every one of those 124 million dials, LoRA freezes the base model completely and adds a tiny set of new trainable parameters called adapter matrices. You typically train less than 1% of the total parameters, sometimes as few as 350,000 out of over 70 million. This means you use far less GPU memory. Training finishes faster, and the base model stays intact. You can even create multiple adapters for different tasks and swap them in and out like changing a drill bit. The adapter itself is just a few megabytes, portable, shareable, and reversible. LoRA is like adding a specialist plugin to a working machine rather than rebuilding the entire machine from scratch. We have covered the theory behind LoRA. Now let us see the full workflow in practice. We will load FLAN-T5 and SAMSum, configure LoRA, train for 3 epochs, and test the fine-tuned model on new data. Now let us see LoRA in action. We will fine-tune FLAN-T5 Small, a 77 million parameter model from Google, using LoRA. We load the SAMSum dialog dataset, configure LoRA with less than 1% trainable parameters, train for 3 epochs on a T4 GPU, save the adapter, and test it on a new conversation. This is the complete workflow, from dataset to trained adapter, in under 5 minutes. We are using the SAMSum dataset. SAMSum contains real messenger-style conversations, casual chats between friends, paired with human-written one-line summaries. 500 training examples. Each one teaches the model to compress a dialogue into a single sentence. For example, Amanda offers cookies, Jerry says yes, Tom asks for one, and the summary captures exactly that in one line. This is the data that will teach FLAN-T5 how to summarize conversations. Here's the setup code. We install PEFT and import the libraries. We load SAMSum, 500 messenger conversations with human summaries, and FLAN-T5 Small from Hugging Face. 77 million parameters already instruction-tuned. Now watch it execute. Dataset loaded. Here is a sample about baking cookies with its summary. The model downloads from Hugging Face. Parameter count confirmed. Everything is ready. The tokenization function. Each dialog gets prefixed with summarize : The tokenizer converts text to input ID with padding. Labels are the target summaries. Now LoRA configuration. Rank 8, Alpha 16, targeting query and value layers. The base model stays frozen, only 353,000 trainable parameters. Watch. The tokenizer processes 500 examples. Then the critical output, 353,000 trainable parameters out of 77 million. Less than half of 1%. Now the training begins. Before we watch it run, let me explain what these numbers mean. The model has 77 million parameters. Think of parameters as tiny dials inside the model. During normal training, every dial gets turned to reduce errors. But with LoRA, we freeze all 77 million dials and only add a few new ones, just 353,000. That is less than half of 1%. Those new dials are the LoRA adapter. Now, 3 epochs. An epoch means the model looks at every single training example once. So 3 epochs means it will study all 500 SAMSum conversations 3 times over. Batch size is 4, which means the model processes 4 conversations at a time before updating those LoRA dials. But we also have gradient accumulation of 4. This means the model collects updates from 4-minute batches and only applies them once, effectively giving us a batch size of 16. This uses less GPU memory while still getting the benefit of a larger batch. The learning rate, 3 times 10 to the power of -4, controls how big each adjustment to the dials is. Too big and the model overshoots. Too small and training takes forever. Now watch the loss. Loss is simply a number that tells us how wrong the model's summaries are. Lower is better. It starts around 3.5 because the model has never seen SAMSum conversations before. Every training step, the model makes a prediction, calculates its error, and adjusts the LoRA dials slightly to reduce that error. Step by step, the loss drops. By step 10, it is 2.5. By step 20, it reaches 2.0. The adapter is figuring out the pattern casual chat in one-line summary out. Around step 30, the loss is below 1.7. Epoch 2 begins. The model sees all 500 examples again and continues improving. Loss drops to 1.1, then below 1. Final epoch. Loss stabilizes around 0.9. The model can no longer improve much on this data. Training complete. In 2 minutes on a T4 GPU, our LoRA adapter learned to summarize messenger conversations. The model is no longer a general-purpose language model. It is now a SAMSum dialogue summarizer. We save the adapter with save_pretrained. Only the LoRA weights are saved, not the entire model, just a few megabytes. Now the real test. We give the model a brand new conversation it has never seen before. Amanda says she baked cookies and asks if anyone wants some. Jerry says yes please. Tom asks to save one for him. Before fine-tuning, the base FLAN-T5 model would produce a generic or irrelevant response because it has no idea what SAMSum summaries look like. But our fine-tuned model immediately generates a concise one-line summary. Amanda baked cookies and offered them to Jerry and Tom. That is exactly the kind of summary the SAMSum dataset expects. This single test proves the training worked. The LoRA adapter taught the model to understand and summarize casual messenger conversations. So how do you choose? Here is a simple framework. Use RAG when the model needs facts, fresh knowledge, document search, or source citations. For example, answering questions from hospital policy manuals or searching legal contracts. Use fine-tuning when the model needs entirely new behavior that RAG cannot provide, learning a specialized output format, mastering a complex domain like drug discovery, or generating code in a proprietary framework. Use LoRA when you need the benefits of fine-tuning, but full training is too expensive, or when you need to maintain multiple specialized versions of the same model. And for the most demanding use cases, combine RAG with LoRA, give the model both external knowledge through retrieval and adapted behavior through the LoRA adapter. No single method is always best. The right strategy depends on what your problem actually needs.